Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Saya Nur Afina Farisha binti Edi Rusdi bersama pasangan saya, Syaira binti Abdul Ghani. Kami ingin membentangkan projek yang diberi oleh Dr. Iliani Abdullah iaitu persamaan pembezaan. What is differential equation? A differential equation is equation that relate with one or more of its derivative. This means their solution is a function. It is divided to two types, which is ordinary differential equation (ODE) and partial differential equation (PDE). ODE is differential equation containing one or more functions of one independent variables and its derivatives. The term ordinary is used in contrast with the term PDE, which may be with respect to more than one independent variable. PDE is differential equation that contains beforehand unknown multivariable functions and their partial derivatives. It is used to formulate problems involving functions of several variables and are either solved by hand or used to create a computer model. ODE and PDE can be different by their writing. Formula of ODE. First equation is called first order since it involves the first derivative. Then, second equation is called second order because it involves the second derivatives. Next, third equation is called third order because it involves the third derivatives. Same goes to the nth order since it involves the nth derivatives. What are the properties or characteristics of ordinary differential equation ODE? It consists of two theorems, which is Theorem 1, existent properties, and Theorem 2, uniqueness of properties. For Theorem 1, suppose that fxy is a continuous function defined in some region containing the point x0, y0, then there exists a number delta 1, possibly smaller than delta, so that a solution y equal to fx to ampersand is defined for x0 minus delta 1 smaller than x0 plus delta 1. For Theorem 2, suppose that both fxy and delta f over delta y xy are continuous functions defined on a region R as in Theorem 1. Then there exists a number delta 2 possibly smaller than delta 1 so that the solution y equals to fx to ampersand, whose existence was guaranteed by Theorem 1, is the unique solution to ampersand for x0 minus delta 2 smaller than x0 plus delta 2. Discuss the solution of differential equation and role of constants. To get the general solution for differential equation, we have to integrate. The example, dy over dx equals to sin x minus 4 and y equals to negative cos x minus 4x plus c. Many people are curious about the existence of c or constants at the end of our integral solution equation. It is important. These constants expresses an ambiguity inherent in the construction of antiderivatives. If a function fx is defined on an interval and fx is an antiderivative of fx, then the set of all antiderivatives of fx is given by functions fx plus c, where c is an arbitrary constant. The constants of integration is sometimes omitted in list of integrals for simplicity. Explain all the methods to solve ODE. The methods to solve ODE, there are a few. To name such: separable, linear first order, homogeneous of order 0, exact, Euler, matrix, Picard iteration, and Taylor series. As for us, we are going to show you about two methods, which is Picard iteration method and Taylor series. For Picard method is an iterative method. An iterative method gives a sequence of approximation y1x, y2x till ykx. to the solution of differential equations such that the nth approximation is obtained from one or more previous approximations. The integration of differential equations 1.2 yields this equation. Note that the exact solution of initial value problem is obtained for t equals to t naught. For approximate solution, the exact solution yx is approximated by y naught in the integrand to get this equation. The approximation can be improved as this equation and a sequence of approximations y1x, y2x till ykx can be obtained as this equation. From the theory of differential equations, it can be proved that the above sequence of approximation converge to the exact solution of initial value problem. Example, solve the following differential equation dx over dt equals to dx with x equals to 0 equals to 1 using Picard iteration. X naught t approximately equals to 1. X to t equals to 1 plus integration of 0 to t 1 dot tau d tau equals to 1 plus t squared over 2. And x 3t equals to 1 plus t squared over 2 plus t4 over 8. X 4t equals to 1 plus t squared 2 plus t4 over 8 plus t6 over 48. In this case, the differential equation is separable. We can solve it easily to get xt equals to exponent of t squared over 2. Picard iteration is giving us the power series of this solution. Each iteration gives us an additional term. This is not always the case, as you can see by experimenting with the program in the next section. Taylor series method. The initial value problem gives the solution y0 at initial point t equals to t0. For a given step size h, the solution at t equals to t0 plus h can be computed from Taylor series as this equation. From the differential equation, it is observed that this equation repeated differentiation gives y second order t0, y third order of t0 as this equation, and this equation, and so on. Substituting these derivatives and truncating the series 1.4 gives the approximate solution at t1. For example, obtain the approximate solution yt of initial value problem using Taylor series method. Obtain approximate solution at t equals to 0.1 correct to 4 places of decimal. Y prime equals to 1 plus ty. Y0 equals to 1. Solution, given that y prime equals to 1 plus ty equals to fty. Repeated, differentiations yield this equation, and so on. Y0 equals to 1, y prime 0 equals to 1, and y second order 0 equals to 1, y third order 0 equals to 2, and y fourth order 0 equals to 3. Substitution in 1.4 with t not equals to 0 and h equals to t gives this equation. Taking t equals to 0.1 and substitution in the above series gives this equation. That's all from us. Thanks for watching.